Hello, welcome back again to AP Physics. Today we're going to be talking about forces. F-O-R-C-E-S. Wow, it's been a long day and I spelled forces wrong. All right, so we can get really fancy schmancy with a definition of force. But the easiest thing to say is force is a push or a pull. All right. When you pull on an object, you're applying a force. When you push on an object, you're applying a force. All right. We're going to do Newton's first and second laws today. But before we get into Newton's laws, I have to explain something about Newton's laws. So Newton's laws only hold true in an inertial reference frame. In an inertial, I-N-E-R-T-I-A-L reference frame, F-E-R-E-N-C-E frame. All right, here's what this means. This means an inertial reference frame is any reference frame that is not accelerating. If you try and understand an object's motion and you're in a reference frame that's accelerating, Newton's laws won't help you that much. All right, for example, let me show you something. Let's say I've got a car here, and let's say this car is going around a turn. Okay, so there it is going around a turn. And let's say it's just kind of like part of a loop, okay? So at some instant in time, it's going this way. All right. Now, I'm in the car, I'm belted in, all that kind of stuff. All right, I take and I let go of a ball. There's a ball, and I'm just going to hold it in my hands, and at some point in time, I just let go. Now, here's the dealio. From the ground's reference frame, all right, ground reference frame, RF. Okay, the ground's not accelerating, so that would be an inertial reference frame, and Newton's laws are going to explain what's happening. That's happening. So from the ground's reference frame, what we're seeing is there is a force on the car this way, probably because of the friction between the tires and the ground, which is causing it to change directions. And once I let go of the ball now has no forces. It's not being pushed or pulled, and the ball will continue in a straight path until, of course, it runs into the car. So, outside of the car, here we go. The car and all that's in it, as long as it's held together rigidly, is going around a turn because of this force. Once we let go of the ball, having no force on it, continues to go straight. From the car's reference frames, things don't make sense as far as Newton's laws go. From the car's reference frame, so here we go. I'm going to put a coordinate system on the car. Hey, that's X. Hey, that's Y. All right, and this coordinate system is going to keep going right along with the car. What happens is there is a force being applied to the car that is causing the car to do nothing. That's the only force. It's an unbalanced force. Well, there's normal and gravity down, but those are going to cancel out. But it's causing the car to not do anything. Because from the car's reference position, reference frame, the car is sitting still. And the world is going by it. All right. Now, from the car's reference frame, the moment I drop that ball, the ball starts coming to the right with no force on it. This ball will change directions without there being a force on it. All right. We are used to Newton's laws. We are used to how it works in inertial reference frames. You push something, and it has if it's a net force, if it's an unbalanced force, it will cause the object to accelerate. In this non-inertial reference frame, this accelerated reference frame, I'm getting an object I'm not pushing, and it's accelerating. It's changing directions. It's basically going woo, through the car. All right. So for Newton's laws, first thing to remember, only holds true in inertial reference frames. All right. Next thing. Let's talk about Newton's first law. All right, Newton's first law. A lot of words to this one. Okay. An object at rest will remain at rest until acted on by an unbalanced force. Excuse me. An object at rest will remain at rest until acted on by an unbalanced force. First thing, first word, this idea of an unbalanced force. Okay? That is a force that doesn't have any other force pointing the other direction to cancel it out, to balance it out. Another word for unbalanced force would be a net force. Okay? An example of an unbalanced force. All right, so let's say, let me do this up high. All right, here we go. Here's an object. If we pull this object with a force equal 5 this way, and nothing pulls back the other direction, that's an unbalanced force. All right, but if we pull this way with a force equal to 8, hey, it's still unbalanced. Because it's tug of war, the 8 wins by how much? 3. The unbalanced force is 3 to the left. Now, if I were to add a second force over here, a force of 3, we're back to being balanced, okay? Unbalanced forces. An object at rest will remain at rest until acted on by an unbalanced force. That's the first part. If they're balanced, it's going to keep. An object at rest will remain at rest as long as the forces are balanced. That's another way to put this. Okay, and here's the second part of this. An object, B-J-E-C-T, in motion will remain in the same straight line constant speed motion until acted on by an unbalanced force. Wow, that's a lot of words. Oops. Okay. An object in motion will remain in motion until acted on, will remain in the same straight line, constant speed motion until acted on by an unbalanced force. In here, the things I want to highlight are straight line and constant speed. Those two things are talking about the velocity. As long as whatever we get the same straight line and constant speed. If it's not changing directions and it's going at the same magnitude, the same speed, you're keeping the same velocity. So an object in motion will keep its same velocity until acted on by an unbalanced force. All right, so here it is. Newton's first law for an object at rest, Newton's first law for an object in motion. We can combine that and cut right to the chase. Here is the abridged version. Version. It's been a long day. All right, here's the abridged one. Okay. And this is really all you need to know. Unbalanced forces cause velocity to change. There it is. All those words are cut right to the chase. Unbalanced forces and the velocities change. Balanced forces, velocities don't change. By the way, an object at rest, that's a zero velocity. Hey, as long as the forces are balanced, it's going to remain zero velocity. All right, the same velocity. Okay, unbalanced forces, velocities change. Balanced forces, velocities don't change. Velocities are constant. That's Newton's first law. It's just a general idea. It's called the law of inertia. Inertia is that property of an object which has it resist changes to its velocity. Okay, there's Newton's first law. Not a whole bunch of problems to go with this. It's just an idea that you got to know. All right. So now that we're done with Newton's first law, let us go, let me flip my page here, to Newton's second law. Newton's second law. Second law. All right, if you really understand Newton's second law, you don't need Newton's first law, because Newton's second law takes that idea of Newton's first law, puts an equation to it, and actually expands on the idea. Here's the equation. There's words, but let's just cut the equation. Force net, so the net force, sometimes is written the unbalanced force, is equal to the mass of an object times its acceleration. So here's the deal. If you apply net force to an object, that object will accelerate. By net force, of course, we mean unbalanced force. If you apply an unbalanced force to an object, it will accelerate. Hey, zero force, zero net force, zero unbalanced force on an object will have an acceleration of 0. All right, so that's Newton's first law, but now with some numbers, so we can start doing stuff. This equation is a vector equation. There is direction with forces, and there is direction with accelerations. And the direction, okay, important idea. That's an equal sign. Equal sign means the stuff on the left is the same as the stuff on the right. All of it. In math, we concentrate on the numbers. The numbers on the left equal the numbers on the right. But in physics, you got to do it all. Both the numbers, the magnitudes on both sides, when you multiply these two together, has to equal that magnitude, and the directions. Hey, the direction of the net force is equal to the direction of the corresponding or the resulting acceleration. Now, this should make sense. All right, let's talk about this. If I've got an object here, and let's say it's moving with some medium velocity, and then along comes a force, and I put this really big force on it. Well, that's going to cause the object, and here's a little later in time, the object is now going to be moving with a bigger velocity. The direction of the force was also equal to the direction of the change in velocity. So if this is velocity initial and this is velocity final, change in velocity is velocity final minus velocity initial. All right, or do it this way. Velocity initial plus change in velocity equals velocity final. All right, back to our little sketch. Here's my velocity initial. Here's my change in velocity, and that's going to equal the velocity final. Little one, big one. Little one plus the change equals the big one. So the force pointed to the right, the change in velocity is to the right. And remember, acceleration is just, well, dv dt, if you want to do it calculus, or we can just say acceleration's change in velocity over change in time. The direction of the change in velocity is the direction of the acceleration. Direction of the change in velocity is always the same as the direction of the force. Okay, these always are in the same direction. That's a straight line one. How about this, just really quick? I got an object going this way, and a force points to the left. It's going to cause this object to turn to the left. The change in the velocity will be to the left. Initial velocity, at some time later, I've got some final velocity. The change goes right this way, which is in the same direction as this, as it's going around. All right, so that's Newton's second law. It's an equation. All right. There are two ways, and I'll do this problem in a second. There are two ways to come up with a net force. Whenever you have a net force in a problem, two ways to come up with it. First is to use Newton's second law. Second is to actually do a vector addition on the forces. So I want to work a little sample problem where I'm going to do the vector addition. You'll see what I mean, okay? All right. So here's the dealio. Let's say I got an object. We always start with an object. Hey, there's an object. And it's got some mass, let's call it 10 kilograms. And I'm going to apply two forces on it, and I'm going to use the forces. I'm just going to make them up because I know what's going to happen. All right, so I'm going to say this is a force of 6 equals 6 newtons. And up this way, we've got a force equal 8 newtons. I want to know what is the third force which will cause this object to have an acceleration of 0. So I don't want it to accelerate. Let's say it's at rest. I want to keep it at rest. What third force do I have to add on which will keep it at rest? Okay, I said there's two ways to come up with a net force. One way is Newton's second law. Here we go. Force net equals mass times acceleration. That's supposed to have T there, all right? Now, I said acceleration must equal 0. Therefore, boom, 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 force net must equal 0. I don't know if you have to do vector, but it's the magnitude 0. All right? So that's one way. I used Newton's second law to come up with the net force. It had to be equal 0. The other way to come up with net force is do a vector addition. All right? The whole idea was, what is the third force I'd have to add to keep this thing from moving? Well, here's how I do it. I'm going to take these two guys and I'm going to find out what the addition of these two vectors is. All right, and it's going to be up in here to the right. All right, so this is, and I'm drawing it light for a reason. So force net between these two guys is going to be the square root of 8 squared plus 6 squared. 8 squared plus 6 squared. And 8 squared plus 6 squared, what's 8? 64 plus 36, that's 100. Square root of 100, 10. All right, so the amount of this is 10. The angle of this, just because I know this, I could do inverse tangent to come up with the angle. But the angle is 36.9 degrees. Okay? That's, when I add up these two, that's what I get. So the force that would balance these, because remember, we want to balance force. See how I'm using vector addition to get this. The force that balances these goes this way. It's got to be a little bit longer. The force must be 10, and it is at an angle of 39.6, no, 30, oh boy, I screwed it up, 36.9 degrees, and that is down from here. If I say this is 0 degrees, it's 36.9 plus 180. Okay? So the other way you can come up with a net force is by doing vector addition. Here, I added those two vectors to come up with the resultant of those two, and what did I have to add to that resultant to wipe the whole thing out? Okay? All right. So that's forces in a nutshell and force balancing. Last thing I want to do is I want to do a ramp problem. Okay, because these are kind of important in physics, and we don't really do a lot of them last year. All right, so how do I want my ramp? Going up and to the right? Yeah, let's go up to the right. Let's go down to the right. Here's my ramp at some angle. Onto the ramp, I'm going to apply some mass. All right, here come the forces. First force we have, because it's on the Earth, you've got some gravity force. Second force you have is the object will not pass through this ramp. And there's going to be what's called a normal force keeping the object from passing through the ramp. And whenever two surfaces mush against each other, press against each other, the resulting force is always at a right angle to the surface. So the force on this mass is at a right angle to the surface that's creating that force. That means there's a force going this way, and this is called the normal force. The normal force. That's it. If there's no friction, those are the two forces, and this object's going to slide down the ramp. Okay? Now, if I want to know the acceleration of this object, again, no friction, it's pretty darn easy. All you got to do is come up with an angle. Let's make the angle easy. Let's say it's 30 degrees. And come up with a gravity force. just because I'm crazy, I'm going to say 10 newtons. Okay. Tomorrow or next time we'll learn how to come up with that number if you don't already know. All right, so I got these two forces. First things first. In this direction, in the normal direction, right here, the forces have to balance. And the reason why they have to balance is because this mass is it's not changing its velocity in this direction. It's not lifting off the ramp. It's not burrowing into the ramp. It's just staying at the same distance away from the center of it. It's staying the same distance away from the ramp the whole time. It has no motion in this direction, and it's continuing to have no motion in this direction. So the normal force and this part right here of the gravity force are going to be balanced. I'm going to call this force gravity in some new y direction. And I'm going to find, hey, there's my new x direction. Hey, here's my new y direction. X is down the ramp. Y is at a right angle to the ramp, or normal to the ramp. All right. These two have to balance. The other force we have, if we're breaking up this gravity force into components, is I've got a force that goes this way. And I'll call this force gravity in some x direction. And I've basically replaced the gravity force with these two parts. This part and this one, gravity in the y and the normal, they're going to balance because no motion in this direction. This force is going to cause the acceleration. So how do we get that force is the question. All right, here we go. Let me switch to an absolutely new color. If this angle is 30, then, trust me on this one, this angle is also 30 degrees. And here's how this works. Think about this. If I were to take this angle and make it 0, go from 30 degrees down to 0, what would happen to this angle is it would go from 30 also down to 0. And I think of this, all right, I'm going to end up being off the screen. I think of this kind of dynamically, right? So here, this pencil is pointing in the direction of that gravity in the y, of that point. I'm going to take, and then straight down, we also have the regular gravity is pointing straight down. As I make the angle smaller, I'm making the ramp smaller, the angle between this pencil and straight down is getting smaller as well. And when the ramp's finally at 0, guess what? This thing points straight down, and there is no angle between the gravity and this gravity in the y. So these two angles go together. All right, so we know that. In doing these components, we've basically made a rectangle where it's a right triangle right up there. All right, well, I guess that's the way rectangles are. So if I want to know the gravity in the x, it's going to be the exact same as this part of my right triangle. See a right triangle here? Oh, I'm seeing a right triangle. I'm seeing a right triangle. All right, here's how we get this side. Force gravity x prime, same as this, because it's two sides of a rectangle, all right, is going to equal the hypotenuse, which is this. So it's force gravity times the sine. This is the opposite side. Opposite goes with sine. Times the sine of the angle. 10 times the sine, 30 degrees. That's going to be 5 newtons. Now I know how much force is pulling this thing down the ramp. The only other thing that I need to know to find the acceleration is, let's say its mass was equal to, I don't know, 2 kilograms. Mass was equal to 2 kilograms. I want to know the acceleration. Force net equals mass times acceleration. Now look, remember, vector equation, mass and acceleration have to go in the same direction. All right, not mass, net force and acceleration. Well, the net force points down the ramp. The acceleration is going to be down the ramp. It's going to go down the ramp faster and faster and faster. All right, acceleration is force net over mass equals 5 over 2, 2.5 meters per second squared. That's the acceleration down the ramp. Okay, that's how ramps work. Eventually we'll put friction in the ramps and get crazy, but right now that's the basis. All right, have I done everything? I pretty much think I've done everything for our introduction to forces. So, having said that, all I have left to say is adios, everyone.